right?
Okay, sorry. It is my fault. Now you have right. You should have right.
Yes, I have. So do you see it?
Yes, perfectly.
Okay, so the overall picture that I'm going to present today is synthesizing the different notions, the notion of well-definedness applied to contracts. So this notion comes from algebraic systems, and combining it with the notion of design by contract and program proving to make sure to establish security of code equipped with contracts. So let me, and the core idea is that secure code must correctly implement a well-defined contract. So I will explain in detail what do I mean by a well-defined contract. But first, let me start with recalling what is a well-defined function. So let's say we have some set S and a collection of equivalence classes inside this set. It may not be a set, actually. It doesn't have to be a set. It can be some sort, but it's convenient to represent this graphically anyway. And so a well-defined function is such a function that preserves the equivalence classes. So it's if two objects from one happen to be in the same equivalence class before, they are still in the same equivalence class after applying the function. And so it's irrelevant, it's wrong, it's prohibited for an object to change its equivalence class. And this idea, this approach, not approach, but this concept has to do with the security somehow, and I will tell you how. So a little bit of my background. I'm currently a remote postdoc in the chair of software and security in Schaffhausen Institute of Technology. So my immediate boss is Bertrand Meyer, who is also my academic supervisor. And I spent around 7 years at Innopolis University, mostly as a researcher, a little bit as an assistant professor, but just a little bit. And I still have some little participation in a project with Innopolis University. So, and my first education is the mechanics and mathematical department of the Novosibirsk State University. So, how do we define secure software? We may have different, we may characterize it differently depending on the scale and on the level of detail so we can say that it does not have stack overruns or does not have SQL injections, but these are very technical definitions. And while we abstract away from this, while we take a broader view, sort of zoom out, we come to a simple definition, which is secure software exposes no undocumented functionality. So there is nothing that it can offer that is not documented as part of its functionality. Let's take an example. So let's say we have a requirement saying depositing X francs on a bank account increases its balance by X. So it's a functional requirement that has a very straightforward and naive implementation, which simply sets the new balance on the account equal to the old balance plus X. And it's quite obviously correct. But this implementation is correct as well. We have added a couple of lines that increase the balance of the programmer who wrote the code just by a little bit, and decrease someone else's balance by the same amount, so that the overall sum does not change. So we say that we call these instructions side effect causing instructions that change the state of the system. It's for the future definitions. So and we come to the observation that the key to security is functional requirements. They should state what the system should do, which is quite obvious, which is natural, but they should only state what the system should do and nothing else. And they, most importantly, they should state all that the system should do. There should be nothing, there should be no open questions left after specifying the functional requirements. And sometimes this may include stating what the system must not change. It's known as frame specifications that say, like the, for example, using the previous example, that the other accounts should not change. It should be stated somehow. So the theoretical basis for what I'm going to present is for logic. I think I assume everyone here is familiar with it. So it's a naive form applied to the procedural programming. Consists of very small set of axioms. It's way more complicated for object-oriented programming for various reasons, but the basis remains. And so this theory has an application. It found its place in programming. So this screenshot depicts Eiffel Studio IDE in the process of programming. So after entering dot to the right of a variable name, we can see the list of available methods. But unlike IDEs for languages like Java, with no contracts, we do not only see the list of available methods with their signatures, but we can also see the contract. So we can see the precondition for the currently selected method and the post condition. So this basically map to the core logic precondition and post condition. So to apply this to the previous example, this requirement finds its place in the current in the following post condition. It says a.balance equals old a.balance plus x. And so yeah, this is a post condition. So there is a tool that that is not still widely used, and it has some usability issues to fix, called autoproof, that can check correctness of programs against their contracts. So on this screen, you can see a simple example, and you can see that the verification of withdraw failed. What do you think? Why did it fail? So this feature is incorrect.
Maybe because of the order of when because somebody can try to withdraw something immediately after previous withdraw, maybe.
There's plus instead of minus.
Yes, exactly. So we have
yes,
plus here, and the contract to have minus. Yes. Thank you, Nikolai. So, and the transfer feature is not visible here, but what it does, it withdraws the amount from the current account and deposits it on some other account that is supplied as a formal argument to the transfer feature. So we can, well, once we have successfully verified a class, we can sort of, so to say, stamp it or certify that it's verified and can be safely used by other classes. So, and that's why this is the symbol of autoproof. It's a stamp, basically. So coming back to the to the main idea of the talk. So by analogy, the analogy of well-definedness in programming is basically a contract is well-defined if it permits a single set of side effects. So I will show you how to operationalize this definition, but basically what it means is that well-defined contracts disallow undocumented functionality. So they do not only capture functional requirements, but they capture them completely. So there is no portion of the state that is not described in the contract. So, and to apply this idea to real code, I took a library called ifl-base2. So it's a library that was fully specified and verified without a proof. And it's not just an arbitrary library. It was specified with a special care. It was specified with a focus on well-definedness of contracts, but well-definedness is called strengths. Contracts are called strong in the corresponding publication. And the idea was to have the contracts as strong as possible. And still, I was able to find a number of contracts that are insufficiently strong or not well defined. So this, yeah, as I said, this library was verified without a proof. It was the best paper. It won the best paper award at Formal Methods 2015, and yeah, one of the statements in the paper is that the pre-verification version of ifl-base2 included complete implementations and strong public functional specifications. So strong is a synonym of what I call well-defined. So let's take a specific example from this library. So it's a feature for copying some object into the current object. So it's inside of the class implementing a two-dimensional array. And so it has the following structure. I'm not listing the implementation because it's irrelevant, but it starts with some if clause, checking if this object is alias to the current one. And the post condition says the following. The array is the linear representation of the two-dimensional array if it's equivalent, object equivalent to the array representation of other, and the column counts are the same. So object equality can be redefined, and yeah, it needs to be checked. I'm going to explain how. But it's different from reference equality. So if we use the traditional equal sign, it means reference equality. So and it was of course verified with autoproof, but there is a problem with this contract. By looking at the structure of the implementation and the post condition, we can say right away that we can notice that the implementation only handles the case when the two objects are not aliased. Other is not aliased to current. And so, of course, for this case, the post condition will hold, but the precondition does not require explicitly that the object should not be aliased. So the precondition only mentions some verification related annotations, but nothing about the non-aliasing of other and current. And so what does it mean? It's possible to exploit this problem by inserting the else clause in the end of if that simply erases the contents of the linear representation and resets the row count and column count attributes. And the contract will still be satisfied because the current object is aliased under this else clause to other. And of course, its sequential representation is equal to the sequential representation of other, and same for column count. Yeah, so this may happen, for example, if the implementation of a class is subcontracted to someone who may not share interests with who wrote the specification, who wrote the contracts, and there may be, in principle, someone who wants to overcome the specification and write some code that does something not expected. So, and this implementation passes auto-proof. So I checked it. I took the implementation of this method with this added code, and it passes verification. And so the solution to this is very simple. We should only add the old keyword on the both lines of the post condition. So this means that the sequential representation should be equal to the sequential representation of other in the old state. So in this case, it will account for the aliasing case, and even if other is aliased to current, then this post condition assertion will reject this code. So how do I even start? How did I even start looking at this feature? Why did it attract my attention? So I'm using a technique that is intended to check well-definedness of features contract. So in this case, the feature is copy and we do copy on objects of class VRA2, which is a two-dimensional array in this library ifl-base2. And because the verification by auto-proof is modular, it can only see the contract of copy. It does not look at its implementation. And so this routine that you can see, VRA2 copy, it's an artificial routine that is never called. But its purpose is, the goal of its existence is to be verified by auto-proof. It's not intended to be run, but it expresses, basically, you can call it a theorem or statement that says for any A1, A2, and other, such that A1 is object equal to A2, that the copy, doing the copy on these two objects preserves their equivalence. And so for the equivalence, auto-proof also can only see only the contract definition of equivalence. So this is how we check whether the contract of copy is well defined. So and if it passes if this whole routine, artificial routine passes verification by auto-proof, This means that the contract of copy is well defined with respect to the equivalence definition, which can be redefined, and we need to make sure that it's adequate. And this method should be repeated for this technique should be repeated for other methods, for other commands of the class that change the state, and for other classes in the library. How do we check adequacy of defining the equivalence? So we introduce another artificial routine. In this case, we array2 item, and we add to the require clause, we add the precondition of item. And the idea is to make sure that assuming the fact that two objects are equivalent, we should be able to infer that queries doing like extracting that the same information is available on both of these objects. So if we take, for example, two integers that are that represent some row and column in the two-dimensional array, the equivalence of two objects leads to implies equivalence of the elements located at this by these coordinates with ing in these objects. So this means that the definition of equivalence should be strong enough. Otherwise, we can simply say that it always returns true, and this will make this this will make this technique useless, because we can always prove true. And that's why we want to be able to infer some useful facts from equivalence. So I was already able to find other contracts of copy in the following classes. So there are 17 different implementations of this feature in 17 different classes, and in 8 of them it's underspecified. And I was actually able to modify the implementation in a nasty way so that it still passes the original contract. And you can see my this code modifications. They're publicly available on GitHub. So I forked the original IFL-based repository, and I'm experimenting with it. So the lessons from the main lessons are that it's not sufficient even to write contracts, although it's very good and it helps develop correct software. It's not enough, because contracts by themselves can be incomplete, can be insufficiently strong or not well defined. I think well defined is the right term to use, because this is what this is how it's called in algebra. So we should not only practice design by contract to make sure that we cannot have bad implementations, but we should check the contracts for well-definedness, and the presence of a program prover can help tremendously to do so. So I'm planning to finish evaluating this technique on IFL-based2 and apply this to more examples, and we should also implement these checks in autoproof. And I don't have formal definition, formal description of this approach. So it's currently it currently remains at the level of code itself. I think it should be formalized and then published somehow with the evidence that it works. And so I have already checked in total 68 different features. 19 of them failed this check, and so 8 of the 19 I was able to exploit. So I have already shown the classes that are definitely prone to this problem. And I need to investigate the other failures of this check. Maybe it's just, so autoproof is not perfect, and it relies on a technology called Boogie, which sometimes cannot prove facts that are true facts. I think it's normal because it's a sound technology, and we cannot have soundness and precision at the same time. Yeah, so the list of completeness checks that I have so far is in the same repository. There is a special class for it, so you can just go and see it. Yeah, thank you for attention.
Thank you, Alexander. We have 10 minutes to discuss, to ask questions and discuss. Any questions, please?
So can I ask something?
Sure.
So in many software high-level specifications, it's actually useful to have a non-determinism. For example, you have a set, and it may be useful just to pick a random element from this set, and many algorithms will work with that. Can you specify that? Because you said that that contracts always must be determinate. So is this?
Yeah, for non-deterministic specifications, I think so my understanding is that if there is a portion of the state that is non-deterministic, then this portion of the state just should not participate in the definition of equality. So that's it. In this case, it will be possible to modify this portion of the state in the ways we want to. It will not be...
But if you, for example, have this random selection of a set, then in the end, the elements that may come out that may be selected may be not equivalent, right? If you, for example, you have, say, something that is randomly ordered, one could imagine that.
Well, if they are ordered, if we have the notion of order, then we can use it. So if we think that it's the order is irrelevant, then we just do not include it in the definition of equality. Yeah. And so on the other hand, speaking about randomness, so if we want to have some random element, we start with specifying some seed, right? And
it is not like this. It's sometimes for many data structures, it is useful to underspecify them, because then it somehow makes the algorithms cleaner when you use them. I was wondering if you can handle that, or have a principal position that should not happen.
Well, if you don't want, if the nature of the task is so that you don't want well-defined contracts, then okay. So you understand the consequences. That it's easy. It will be easier to have mistakes in the code.
But in a sense, they're still well defined. It's just that they're non-deterministic.
So what does it mean then that they're well defined if they're non-deterministic? So I just I didn't think about this yet, but so what if we have such a data structure? So
suppose you have some data structure, you have this in Java, and you have an iterator that iterates through all the elements in this data structure. So this this iterator can, for many algorithms, it doesn't matter in which order it iterates, for example. And so it is just any order that is convenient.
Yes, but is the behavior of the iterator formalized anyhow? Is there any formal
Yeah,
specification?
so the only thing that it would say is that it must touch every element once, and no element is touched more than once. I mean, that would be the specification.
So every element is traversed not more than once, right?
Yes, yes. And there are many algorithms that will just work with such iterators independent of the order. And it's even considered good programming style in object-oriented programming to not rely on order.
Okay, so the specification, I don't know how to write it in contract, but it will be sort of, if we apply the iterator n times, where n is the number of elements, then in the end they will all be traversed
Yes.
exactly once.
Yes.
So if there is a way to specify this, then I believe there should be some way to apply this approach. But I'm afraid the current version of like the current state of contracts is that you cannot capture such properties in contracts.
Yeah, it is very difficult. I tried it and it's difficult.
Right.
Yes.
Thank you for the
Thank
question.
you. Thank you.
More questions, please. We still have some time. If no more questions, I would like to ask a couple of questions. Could you please go to slide number 9? As I remember, number 9. Okay, nice, thank you. Exactly. First, firstly, I would like to ask, the following question. Do you know, research how to prove that some program does nothing but what is specified? Because basically, if to read your requirements here, it is basically, I firstly interpreted these requirements listed on this slide as follows. We need to prove that some program does nothing but what is explicitly specified. For example, if to go back to your example with erasing an array, whipping the array, how to specify that it does nothing, that, for example, it doesn't whip the array. Do you understand my question?
Yeah, so I guess this is what the talk is about. So
yes, I know, but other research. Okay, please.
Other research. Okay, so
maybe I didn't formulate it clearly. Sorry.
I actually I did some search, but I did not do it in very recently. So I did it when the idea first came to my mind. I explained the concept back in 2016, but I just did not apply it to some real big example, and I'm doing this right now. And I have only recently found the connection with security. I thought that well-definedness is exactly what it means to have no undocumented functionality. So, but no, I'm not aware, at least at the level of, in the field of program verification, I'm not aware of such approaches. So I think so. The idea of my approach is to make the specification, the contract, such strong that you just cannot have two implementations that produce different behaviors. So you can still have different ones, but they will their behavior will be equivalent.
Since we still have some time, I would like to ask more concrete question. Not so general. What do you think if we would like to specify that a program does nothing but what is explicitly specified by adding to all other variables that, let me say, to all other variables, just in the post condition equality that the last value is equal to the old value. Will it be correct?
It may help, definitely. And yeah, so what we propose is to fix this at the level of frame specifications. So part of the problem can be fixed at this level, but not the whole problem, because, for example, let's go back to the bank account. Example.
Very famous example.
Yeah, sure. It's very important to have correctly working bank accounts. So we may not say, for example, plus X. Well, a dot balance equals all day balance plus X. For example, let's say we wrote a dot balance is strictly greater. But then if the balance participates in defining the equality of bank accounts, then it will not be enough, because we will not be able to prove that two accounts deposited with the same amount, two equal accounts deposited with the same account will remain equal after the depositing, because we don't know what will be the exact balance after that. So so if we use strict inequality, we know that okay, it's not part of the frame specification because it definitely changes, but the amount of information about how it changes is not sufficient. So another way to perceive this technique, that may be the right way to perceive it, is, for example, when you have two variables A and B of two integer variables that are, they are equal, you expect A plus 1 to be equal to B plus 1 too, right? Assuming, yeah. And so you want to enjoy this property for any type, not only for integers. Yesterday, Bertrand told me that this property is known as referential transparency. So I still need to investigate it, but this may be the right way to explain it. If we have two entities of the same type that we know are equal, then we naturally expect them to remain equal after we do the same thing to both of them. And then yeah, the connection to security is less important in this respect. It's just the connection exists and it's interesting, but it's sort of it's a possible way to attract interest from the practitioners, from the industry, but it's a side effect of the method, so to say.
So thank you, Alexander. It is time to turn to the next presenter, Nikolai Kudasov.
May I ask a question to Alexander?
Dmitry, yes. Dmitry, sorry, since we should maintain well, right time for starting next talk, after well, after this session, you can contact. I'm not going to turn off Zoom. You can ask Alexander after the session. Could you please?
But Nikolai, I will have to disconnect in 15 minutes because.
Okay. Just Nikolai, dear Nikolai Kudasov, mind that one short additional question. Okay, so Dmitry, please ask one additional short question, and Alexander, please be concise.
It's very difficult for me. Okay, but I will try.
Dmitry, please go ahead.
Do you think it is possible to generate automatically security contracts in the future?
I think so. To some, well, not contracts themselves, but the checks that I propose. They will define as checks of this form. This is definitely possible. But then what remains is to write such contracts that will verify, that will make these checks pass the verification. Fully automatic inference, I doubt so, but we now have artificial intelligence. Maybe it can do a miracle. I don't know.
Okay. So thank you both, and thank Nikolai for tolerance. Now it's turn to present Nikolai Kudasov. The title of his talk is Nameless and Scope Safe: the Bruijn notation as a nested data type. Well, please share your screen. Let me check that it is visible. Yes, we can see it.
Yep. Can you hear me also?
Yes.
Okay. I think just a second. Need to remove everything that obstructs my view of the slides. Okay. Okay. Hello, everybody. My name is Nikolai Kudasov, and today I'm going to be talking about this nameless representation of terms and scope safety. So hopefully the ideas, the basic ideas I'm going to be talking about are familiar to everybody here, but I will be reviewing them anyway. And then we'll present this approach that was actually suggested in a paper more than 20 years ago by Richard Bird and Ross Patterson. Yeah, so let's dive into it. So basically, I imagine that at least some of you in the audience have some experience implementing compilers or interpreters, in particular for maybe functional languages or even lambda calculus itself. And if you have done so, or if you have done something even more complicated with those things, like implemented a proof assistant, for example, you might know that it is not very straightforward to get even the simple thing like evaluation of lambda terms correct with the first try, right? So a quick reminder, in lambda calculus, we have terms, and a term can be either a variable like x, y, or z, or it can be a lambda abstraction, which is written lambda x dot t, where x stands for some variable and t is another lambda term that may use this variable x. So this is basically an anonymous function. And then we have an application. So we can apply one term to another just by putting them side by side. Sometimes we'll use parentheses to just make sure which term is applied to which. So here's some examples of lambda terms.
Nikolai, sorry, yep. Should I ask questions later, or I can?
Yeah, if you have any questions, feel free to ask.
So can you go back to the previous
yep.
one? So the application apparently, so T1 is
applied to T2.
Yes. So you cannot have several arguments, right?
So several arguments are modeled by functions that return functions. So you can have, for example, here, 2 is a lambda term, which is lambda s dot lambda z dot then something. So this essentially models a function of 2 arguments, right? It's a function that takes 1 argument and then returns a function that expects the second argument. This is what's called carrying or carried functions. They are very commonly used in functional programming.
So on the previous slide, basically, in the definition of application, T1 and T2 may be applications themselves, right?
Of course, yes.
Okay.
Mm-hmm. So here's another, function. This lambda term 2 basically represents a function of 2 arguments s and z, where s is applied to z twice. So we apply s to z and then we apply s to the result of application again. Another example is a constant function, which takes 2 arguments and returns the first one. Again, we just model that by 2 lambdas. And here is a famous s combinator, but I'm not going to stop on this one here. Now, when you evaluate lambda terms, you do it with a very simple rule. There's really just one important rule for us. This is the rule of beta reduction. And the idea is that if you have a function, this anonymous function, lambda x dot t1, and you apply it to some other term t2, then to evaluate this application, you just take the body of the function, which is the term t1, and you substitute every occurrence of the variable x in that term with term t2, right? So this is essentially what happens with mathematical functions, and this is what we expect. So here's an example. We may have this function 2 from before, lambda term 2, applied to f. So what happens is we take the body of this function. We take the body of this function, and we need to, and the body of this function is lambda z dot s applied to s of z, and we need to substitute f for s. So we replace every occurrence of s with f, and that's how we proceed in lambda calculus. Okay, very good. Now, so the substitution is at the core of evaluating lambda terms. However, there's a problem. When you try to sort of work with this, you very quickly realize that it's actually a little bit tricky. So for example, here we're applying a term lambda x, lambda y, x applied to y, and then again applied to y. This is the whole term that is applied to another y. So if we try to evaluate this, we see that the body of this function has to have x replaced with y. But if we do that, we get a term where this y, which originally was outside of this term, so it was some variable available in the outer scope, but now that we replaced x with y, it now references the local variable of that function, which is a different thing. So this is not what we want, and this problem is known as capturing a variable, and we want to avoid name captures like this. And a standard way to deal with this is to introduce what's called an alpha equivalence convention. So under alpha equivalence, you say that, well, names of locally bound variables do not matter. So if you have a term where you have functions and they have local variables, you're free to rename them, and the meaning of that term will not change. And you, in fact, consider these two terms equal. So you just rename local variable x to a and local variable y to b, and this is what you get. Now notice that the last y is not renamed because it is not local to that function, and we do not have the binder in scope for that y. So it remains the same. Now this is not equal to, for example, this term. So we cannot simply rename y in the original term to x, because then again, a name capture will happen, and we will now have this x's inside referencing the same lambda and not two different ones. Not sure if there are some questions in the chat.
No. Basically, there is
Okay.
comment to allow speaker to speak, to present.
Okay, very good. So hopefully this is understandable and standard things so far. So now if we want to do the substitution, we whenever we have this problem where what we're trying to substitute actually might result in a name capture. So what we do is we rename locally bound variable to something else. For example, here we rename y to z, and then we can proceed as normally. So this is how it is done on paper. Now, when you try to implement this in a program, so we're going to be using short snippets in Haskell here. What you can do is you can represent a term of lambda calculus as an algebraic data type. So a term, and then this data type is going to be parameterized by the type of identifiers of variables, basically. So a term can be either a variable, or it can be an abstraction. An abstraction consists of an identifier and a term that composes the body of that lambda abstraction. Or it can be an application, which is just two terms, right? Now, you can use, for example, as an identifier a string, and then we can represent this term. Again, lambda s, lambda z, s applied to s of z. We can represent it as a term that consists of an abstraction, of an abstraction, of an application of S to an application of S to Z. So hopefully this makes sense. Now, I don't expect you to be proficient in Haskell here, but generally the structure of this code should make sense to you. So how do you then deal with this? Well, evaluation or this call by name evaluation, for example, can be very easily implemented like this. And again, the details here are not very important. What's important is that we are using substitute function here. And substitute is, well, the substitution. So if you were to implement substitution, you would take a name of the variable that you're trying to substitute, the argument term, which is going to be replacing that variable, and the term where you would like the replacements to happen. And then you basically do the structural recursion. So you check, okay, is my term a variable? If it is a variable that I want to replace, well, replace it. If it is not a variable that I want to replace, then just leave it as is. Do not change anything. If it is an application, then perform substitution in each of the subterms. If it is an abstraction, now this is where it gets a little bit tricky, right? Because then we have to consider several cases. What if the variable that we're abstracting over, so the local variable introduced in that abstraction, is the variable that we're trying to substitute? Well, in this case, what happens is essentially this local variable shadows the variable we're trying to substitute, so we don't have to do anything with the body and we just leave the term as is. On the other hand, if this variable is not equal to the one that we're substituting, so we need to go inside. But if this variable is an element of the free variable set of arguments, which is a very complicated way of saying that there is going to be a problem if we just substitute it there. What we need to do is before substituting, we need to rename this variable. And so I use rename apps function here, which sort of is supposed to deal with the renaming for me. And then if the capture is not going to happen, then we can just substitute in the body recursively. Now, I do not show you the implementation of rename apps, but if you go and try to implement it, with a very high probability, you're going to fail to do it correctly, as I have done multiple times in the past. Well, I'm sure that if you, at any given moment in time, ask me to implement it using identifiers like strings, there's a very high probability that I will not get it completely correct with the first attempt. So it is a good exercise to try and think of, well, what might go wrong here. But again, I'm not showing you the entire implementation because it is huge. It is maybe not huge, but it is like 3 times bigger than what you have right now on the screen. And still it has a problem which has to be fixed. So to avoid dealing with name captures, people have been using what's called De Bruijn notation for quite a while now. So De Bruijn notation is mainly not for humans, but for computers to deal with this, well, more easily. So in De Bruijn notation, instead of using variable names, we're now using indices. And these indices tell us where this particular variable has been introduced by which lambda. So now lambda abstraction does not have an associated identifier. It just introduces a new scope. And then we have an application. Now, here is a comparison, again, of the familiar term, both in the traditional notation and De Bruijn notation. So 0 here means that we are referencing the innermost scope accessible from that term. Now, S of 0, which is the successor of 0, which is essentially 1, this is the index of the second lambda binder that is accessible from the current term. So it references this. Now you can compare this with how Z is referencing lambda Z, and S's, both S variables reference lambda S. Okay. Hopefully this makes sense. Now this, I'm gonna skip this. So how do you perform substitution now? Well, it's sort of the same, but now if you want to perform a substitution inside of a lambda, what you are no longer substituting the same variable. You're no longer substituting 0, because once you enter the scope, whatever 0 referenced now has to be referenced with S of 0, because we are entering the scope, and now to reference something outside the scope, we have to increment the index. So in fact, you need to do this both for the variable that you're trying to substitute and the argument which this variable is going to be replaced with. So you have to, when you go inside of the lambda, inside of the abstraction, you're now not substituting 0 for lambda SS0, but you're substituting S0 for lambda SSS0. So, and then you get something like this. Okay, very good. Again, maybe, I hope it makes sense so far. If you have any question or if you're confused, please ask a question. Okay, so now if we go back to the implementation, the term now can be represented again as a variable or an abstraction or an application, but now a variable is now just an index, which is an integer or a natural number, more specifically, or it's going to be an abstraction, but in the abstraction case, we no longer have the identifier for the variable. Okay, so far so good. So how does this change the implementation of substitution? So the eval function does not really change, but substitution changes. So now it does require something. So as I've mentioned before, when you do the recursive call, which is at the bottom line here, when you do the recursive call for the abstraction, you need to perform substitution, but now you need to increase the index of the variable that you're substituting. And you also need to increase all of the indices for the free variables, but that's a technicality, in the argument. So that's what you see in the bottom line here. Now to increase all of these free variables in an argument, we have this helper function. Now both of these functions are very easy to write, and this is all you need to perform substitution with the De Bruijn indices. However, this implementation, again, even though it is very simple to write, it still contains an error. It is way easier to fix than in the previous implementation, but it still is there. Okay. So now, hopefully you're caught up with lambda calculus, with scopes, and you now understand or are reminded of De Bruijn indices and how they work. And so finally, we go from De Bruijn indices to something else. Now, to go there, first notice that an index, which is a natural number, can be also represented in a different way using an algebraic data type with which is going to be either 0, z, or a successor s of another natural number. So this is more closely correlated with how we wrote it in the mathematical notation. But now, if we just push a little bit further, and if we change this to something slightly different, so what we do here is we make a data type called inc, which is either 0 or a successor of its parameter. So inc A is basically the one extension of the type A. So you can think of it like this. The type A represents the type of possible identifiers that can be used in a term. Inc A basically extends the set of these available variables by one extra variable. In other words, let me show this slide first. In other words, you use this inc A to represent the set of possible variables inside of a scope, inside of a lambda abstraction. So if in a term you have variables like x, y, z, then now when you enter a lambda abstraction with a bound variable, the set of available variables inside of the body of that lambda abstraction is now increased by exactly one possible value, which is here represented by bound or by z. So to do that, in the definition of the term, we're using the technique that is called polymorphic recursion, or it's also known as non-uniform recursion or nested data type. So notice here that the term A is defined recursively in terms of term, but with a different type parameter. Okay. So again, this says that a term over the set of variables that is represented by this type parameter A is either a variable within a value from that set A, or it's an abstraction where the body is encoded as a term where the set of variables is extended by one extra value. And application is unchanged. Okay, so that's basically the interesting idea. So how does it then, what is it good for? Well, the good thing here is that now you are, the type system in Haskell in particular, controls the number of scopes that you have. So if you, for example, have an example of this term where S of Z is used, now this S of Z references some lambda which is not present in this term. So it is basically leaks outside. And such a term can be called ill-scoped because we have a variable that references something that is not in this term. So if you try to do this in Haskell with this new data type, what you will get is a type error, which tells you correctly that, well, you have you have a variable that references something outside of your term. So this is good because now if you have a term, you know that it is well scoped. So every variable, it has a binder associated with it. So I don't think I have much time left. Yes or no? I don't remember how much time I have. Nikolai? how much
Sorry,
time?
I should unmute myself first. You still have 15 minutes. Don't worry.
Okay.
15 minutes.
Okay, very good. So again, evaluating with these nested data types is just as easy. You do the same thing. The substitution at the first glance takes more code. So there's like 2 pages of code. However, what we need to do is we need to, again, be able to increment all of the free variables inside of an argument when we are going inside of a lambda. But to do that, we need to simply be able to convert all of the variables that we have into free variables in the scoped term. So really, we just need to add this extra free or extra successor to every variable inside. And with our new formulation, this actually looks very nicely. So of course, you could have done, we have done similarly with the previous one, but here the types in particular look very nice. If you look at the types, this lift with and with inc both have the type of the form apply a function from A to B. Well, we give it a function from A to B. We give it a term with variables in the set or in the type A, and the result is going to be a term with variables in the type B. So this, a function of this form, we see it for inc and we see it for term, and this is a very common pattern, which is essentially a map function, right? Apply a function to every element in a container. Now, in this case, we have a particularly interesting container. We have a syntactic tree where what is contained is in this syntactic tree are the variables. And so lived with and with inc just are regular old variations of the map function that we can use. And in fact, in Haskell, we could actually derive implementations of these functions altogether. So this entire first list is just a common pattern in functional programming, which in Haskell in particular can be automated entirely. And then the substitution itself, well, again, we're going to do this substitute with, which is a generalized substitution, which tells us for every variable in the original term, which term should it be replaced with. So sometimes we can replace a term with just itself, a variable with just a variable, but other terms can be replaced. And again, the type of this function is something that is very well known by functional programmers and Haskell programmers in particular. This type is exactly the type of the bind operator in the monad type class. So essentially, the term as a syntactic tree is a monad, and this operation is simply extending the leaves of a syntactic tree with subtrees. So this is what's called tree concatenation. And again, a very standard thing. So even though we have to write this code, this one is not automated, at least if you just use it, the definitions that I gave you. But still, this is a very standard code that is very hard to mess up. Again, because the types help you. So really, the implementation of substitution with this formulation is very hard to get wrong. The compiler will tell you if you are doing it incorrectly. So now, basically, the benefits of, well, let me summarize this in a second. I think I have still time. So what else can we do with this deploy notation? Well, note that when we have to increment every element in every free variable in the argument when we are going inside of a lambda, sometimes we need to apply this successor to an entire term. But that means that this term will never have any occurrences of the bound variable. We're just putting it inside of the scope. So instead of applying a successor to every free variable, what we can do is we can modify our idea of what a scope is. So previously, the scope was basically a term f, a term where the set or the type of all variables was extended by one variable. So we can adjust our definition of scope just a little bit to make it so that it is a term where the set of variables is actually the set of all terms extended also with one extra bound variables. Now, this looks a little bit weird, but it might be better understood if we look at just lambda calculus. So here we have a function lambda with a blue body applied to the red argument. Now, to perform this application, we need to substitute 0, or basically the term that referred to this black lambda in the original term, with this red body. Now, here we don't have here to substitute in place of S0. So basically S0 here pointed to that black lambda. So we need to replace S0 with this red term. But this S0 is located inside of a lambda. So we will have to increment all of the free occurrences of all free variables in the red term. However, with this new formulation of the scope, we can just apply successor not to a variable, but to the entire term. Okay, so that's what it corresponds to syntactically. Now, of course, you can propagate this successor if you want to, if this is what is needed. But until you need to do that, you don't really have to do it. This basically is a sort of optimization that can keep your terms smaller and can reduce the amount of traversals that you need to do when you work with these terms. So there are a couple of other generalizations that we can make. So for example, instead of just having a single bound variable, we can have bound variables that are indexed by a type B, and then basically if we use a unit type, basically equivalent of a singleton set for the index, then we have exactly one bound variable. If we're using a Boolean with two possible values, then essentially we have a definition of a scope that introduces two bound variables. If we use an integer, then we have an arbitrarily many bound variables. So all of these has been implemented in Haskell and of course written about, as I've said at the beginning of the talk. All of this has been implemented in Haskell by other people. And I'm just fascinated by this idea, and I do not see it used very often in practice. In fact, I do not think that many people know about it or have tried to use it, even though it seems like it offers a lot of great things, in particular for prototyping languages and interpreters and proof assistants and whatever else. Now, there are, of course, since the original paper, there have been other papers that develop similar ideas. In particular, Conor McBride's "Everybody's Got to Be Somewhere" is again, he introduces another variation of De Bruijn indices, which he calls co-De Bruijn. And the idea is that whereas in De Bruijn indices, we have these successors applied to variables, and in this De Bruijn indices as nested data types, they can be anywhere. In his work, he implements a variation where these successors are always guaranteed to be applied as early as possible, so that you immediately can know whether some subterm does not use a bound variable. So you can very easily syntactically check whether you have, for example, a body of a lambda function that doesn't use its argument. which can be sometimes very useful. So the summary is that these generalized De Bruijn indices are a tool that allows you to provide intrinsically well-scoped terms. So this is basically an improvement of sorts over traditional named-based terms and De Bruijn, traditional De Bruijn notation. If we extend our idea of the scope a bit further, we can provide also efficient substitution and limit the amount of traversal that we have. And in general, this provides us with a tool to handle scopes in a language agnostic way. So I've been talking obviously about lambda calculus, but you can do exactly the same things with different function definitions, with let expressions, or with dependent types like pi types or sigma types. You don't necessarily work with lambdas. And and there are different variations of this technique available. So there are things that maybe, if somebody's interested in this, maybe can be improved or researched about this approach. One is obviously having a data type like that, basically representing piano numbers, is not very efficient. So perhaps there might be some efficient implementation of this technique using some sort of machine integers with phantom types, or maybe something else. And I'm currently using this technique in combination with some other cool things to actually implement a generic higher order unification library. So the idea is that, again, you would be able, since you can talk about scopes, language without considering what exact language you're talking about, like lambda calculus, simply type lambda calculus, dependent type theory, or something else. You can handle scopes, so it allows you to talk about higher order unification and guessing scopes, etc., etc. So it is a work in progress, but if you are interested, feel free to contact me. Okay, that's it.
Thank you
Do you
very
have
much.
any questions?
Thank you very much indeed. We still have some time for questions because the next speaker does not show yet. So please, any questions, comments? There's already a nice comment in the chat. Very interesting. Thanks. Understand De Bruijn part permits to automate rewriting. So, any questions?
I ask a question.
Sure.
What are disadvantages of De Bruijn notation?
It's not human readable. So it's for machines, not for humans. So you have to definitely convert from human readable named representation to De Bruijn, and then you have to you want to store the you want the names that are assigned somehow corresponding to whatever the user input originally. So you have to store it somewhere. So if you want it more user friendly, then there are still tricky situations. But again, with generalized things, it is way more easier to do. Other disadvantages, so for traditional De Bruijn, they are, of course, more efficient than name-based. But if you go to these generalized De Bruijn, then by default, they are, of course, slower than dealing with machine integers. That's why
you have to do something with global. If you have free variables, you have to do something with them.
If you have free variables, sorry.
It was also asked in the chat. But,
if you have, so you have basically, when you have this formulation, you have this term with the parameter A, and this type A is the type of the free variables in this term. Okay. So all of the bound ones are introduced by this generalized De Bruijn, and A is for all of the free variables. Does it make sense?
Yes. Can maybe if I'm anyway, if you're supposed to have types lambda calculus, then the variables need to be typed. Can you deal with that?
The generalized De Bruijn is only about scopes, so it doesn't care about types. Yeah. But of course, when you care about types, well, you just make a more complicated language.
Yes.
Now, I personally am interested in dependent types. Yes. And the general way that you do this is you have you have sort of something that's similar to, I think, Robert Harper's computational type theory, where you basically just throw types and terms and whatever else you have into a single huge data type, and then you have type checking separate.
Yeah,
now, another approach
need to contain the types then. Right.
Yeah, of course, and then you do this dynamically. Yeah. Now, another approach, which is what Conor McBride is doing, and some other people, is they are using what's called higher order abstract syntax, where they are using the type system of the host language to enforce type safety in the terms of the interpreted language, right? So, and they often are using Agda, not Haskell, because again, they are sometimes interested in more powerful languages. And if you're using this higher order abstract syntax, then Haskell cannot be used to express anything about dependently typed languages. It's not powerful enough, right? So yeah, Conor McBride has a lot of things on that. There is a paper, I don't remember exactly the title, but it's something about a universe of type safe and scope safe syntaxes. And they are combining this idea with higher order abstract syntax, allowing for both type safe and scope safe term syntaxes described in Agda programming language.
More questions and comments, please. Since we still are waiting the next speaker, I'll try to contact him, but no response, unfortunately. So more questions, more comments, please.
Maybe one comment for me. It was a great lecture, but it was hard to follow because a lot of things. And could you please upload your Haskell code with some tests so one could follow it by using Haskell? And for me, it would be nice to follow your code and by myself check your things.
Okay, I have the code, but I will add some comments in the code, yes. And then I will send this to Nikolai, and he will share this somewhere.
Okay, thank you.
Moreover, I would like to suggest Nikolai. I am also Nikolai, but I would like to suggest another Nikolai to present his talk with more details. In particular, I would like to attend once again in our online seminar, bi-weekly seminar. So please think about it. Please think about it, because for me it is also too fast. So thank you in advance, by the way. But I also have a question, very naive, but nevertheless related. Several times you mentioned that this approach is more efficient. Generalized De Bruijn indexes are not so efficient, but efficiency always has measurement. So what do you mean this time?
Time and memory consumption.
So do you have some estimation, some theoretical or something like this?
Yeah, so if you, well, one example is, let me see. Let me see. So the problem is when you have this, let me see another type. So when you have this inc type, right? It is basically a tag Z or S, and if it's an S, then it has extra data with it. So it has a tag and then maybe a pointer to the next, to the value of type A. And so when you are, say, 20 scopes inside of some term, right? Then you have this 20 extra levels of indirection instead of just one integer. which is not very bad per se, but it might be not perfect. Now, what is interesting is that in generalized De Bruijn indices, you don't have to always traverse the term. So when you use this thing, when you can apply successor to an entire term, then you don't have to traverse it. So in some situations, this means that you're not doing some extra work, right? However, whether this will help with your performance or not really depends on how much are you relying on this, so what your actual terms are. I think that in a lot of situations you have I cannot provide you with any numbers, but I think that in most common situations in type checking, you have small terms which are shallow and which are not, where you don't really care about this, and you get the overhead of this extra indirectness affecting you much more. But then if you go to large terms, occasionally there maybe you will have some
future overhead.
With large terms, you might have overhead with traditional De Bruijn because you have to traverse everything inside of those large terms. And so then the overhead of this indirectness pays off because you don't have to do extra work. You're more lazy, let's say. But again, I think that if one were to set a goal of optimizing this so that the interface for the programmer is this generalized De Bruijn notation, and then under the hood, it actually uses some efficient implementation, I think that should be possible. It's just that nobody bothered to. And I most certainly will not bother in the near future because I'm most interested in the function, not in performance for now.
Thank you very much. Thank you very much. Any other question, comment, suggestion? Well,
yeah, I made one time an implementation in C++ of the Bruijn indices because I wanted to verify that. It's not
interesting.
But I used a lazy approach. So when you have this lifting operator, I did it somehow lazily. That's not, but I think Haskell is automatically lazy, right?
Yes.
Yeah.
So thanks everyone. Since we still don't have any notice from the next speaker and he still doesn't show, well, I believe that we should, close this session. Sorry about this. Sorry about this. Maybe, Nikolai, do you have any other than Telegram contact with Igor?
Other than Telegram, no.
No, I contacted him, no answer today.
So does that mean that I'm the next speaker in 1 hour?
Yes, in 1 hour. So you are the next, I believe.
Okay.
Thank you, thank you. Hope to see you. Hope you will be on time.
Yes.
So you may. I stop recording.
Yes.
I
We
also
see you and we listen. We hear you.
And I see the recording is in progress as well.
Please show the first slide.
Yes.
So the first talk is made by Hans. Sorry, I am afraid I will not produce your name correctly. Nivelle?
Yeah, Nivelle, that's right.
Yes. A recursive inclusion checker for recursively defined subtypes. Please, it is a regular talk. Thank you very much, please.
So, hello, so my name is Hans Nivelle. I'm from Nazarbayev University in Kazakhstan. I think I will switch off the camera during the talk. That's better for the connection. So I will wait 1 second. So is it better? I think it's better. So I'm going to speak about a recursive inclusion checker, and as one of the reviewers pointed out, this doesn't completely cover the contents, but I kept the title. I will come to that. So okay, so I tell what this is. This is a long-term project, and which until now, which I think is now about to get real results, to design a programming language that is nice to use for logicians. And this is my long and I think about things like field improvers, normal form transformations, verification, lambda calculus, normalizations, and these things are difficult to implement in existing programming languages. So there exist languages which are optimized for logic, like one was just mentioned in the previous talk, like Haskell, and there is also Scala or OCaml, but I do not find them so nice to use, and I will explain why. So my goal is to develop a language that is nice to use for logicians. So, and I plan to give much motivation and little technicality a bit at the end. And yes, so okay. So what the question is, what is special about logic? What makes it different from other things? And so logic makes a very big use of recursively defined data structures with many constructors that are very different. So you can have 10 constructors, and each of them has different types. You can have mutual recursions, and that makes logic, that is special about logic. So here is an example. This is just this is a simple example. So we have a set of function symbols, and then we define terms over them. So you have T1 up to Tn terms and a function symbol, and then you construct a new term. So these are just trees, of course, from the implementation point of view. And there is only one type, so that's okay, but let's do a bigger one. So this is just the definition of first order logic, how you would find it in a textbook. So you have a predicate symbol, you have terms which were defined on the previous slide, and then you can build a formula with them. Then you have say two terms, and you can build a formula with them, equality. Then you have true and false constants. You have negation on one formula. Okay, then you have disjunction and conjunction, and they're usually, I mean, there's no reason to restrict them to 2 arguments, so they can have any number of arguments. And then you have implication and equivalence, which are fixed to 2 arguments. Oh, yeah. And then there are quantifiers, which bind the variable. Yeah, and this is still simplified, because if you would do it for real, you would add types here. So these quantifiers would be typed, and then I would have to give a definition of type to it, and then it would be another slide. So I decided to keep it down. But so these are the things that you see in logic. So then you can look at a couple of existing languages. Of course, not everyone likes C++. So what you see in C++ is you get very long and repetitive code between different inductive types. So there are things like printing, testing of equality, checking size of a formula. It's all the same in principle, but in C++ you cannot share this code. So and if you want, say, to if you have, so suppose you have a formula, let's suppose that, and you want to get and you decide that you establish that it is an implication, and you want to get this F1. So what in C++, what you have to do is you have to cast it first to the subtype of this implication, and then only you can get the fields. And so you have to override the type system, and it's not nice. Yeah, and you cannot regroup cases in different ways. So sometimes let's look at those. So sometimes you may want to treat them the same. You want just to say it's a monotonic formula or an n-ary formula. And sometimes you want to treat them separately, and that's difficult. And the same here. So sometimes you just care only about the fact that it's a binary formula, and sometimes you care about the concrete one that you actually have. And then this is not easy to get. No, so Python, let me shortly speak about this. It gives you a lot of misery with reference semantics, which means that you have unwanted sharing. And it has automatic memory management that is kind of cool. But, in C++ it's semi-automatic, so I think it's not a significant, not a big advantage. So Python has no static type and it's disgustingly slow. That's what I find. And actually in the edit reload cycle is much slower than edit recompile. I find say development in Python annoying because it's just the cycle between trying out and changing the code is much actually slower than in a compiled language. So, okay, then we have Haskell. It was mentioned. So Haskell has inductive types. That's nice. So you can, in principle, write constructors for all of this, define the types and write this. So that's good. Then, here. Then, but for example, you cannot write concrete formulas in an acceptable way because you always have to write the constructors. And the type system is very rigid about this. So it's if you want to write a concrete formula, it's annoying. So okay, then matching is kind of nice. Haskell and also other functional languages like what is the one, Scala offer matching. That's very nice. But this is only if you want to say classify exactly with matching. You want to partition the possible formulas into possible constructors and then get the subterms simultaneously. And this is only nice if you exactly want to follow the constructors that you have. If you want to do it in a different way, it's not nice. And I mean, for example, here you can, these are different constructors and you have to make a principal choice, right? If you're using Haskell, you can either say this is a binary formula, both are binary formula, then you have to put some kind of tag that remembers what type, or you say they're different constructors and then they're forever different, then you can never treat them the same anymore. So in Haskell, you already have to compromise. Okay. So now then, since I became a bit interested in programming language design, what is actually the root cause of all these problems? But this is a bit off topic. I think it's the following. So we have three fundamental type constructors in programming languages. So one is the product. So you have a couple of types and you put them together. So this is completely solved since 90s, maybe even 80s. You have struct and class, you have records, you have tuples and pair, and it's totally fine. Okay, and then we have union, and this is really the big nightmare, that this is just unsolved. We have, for example, in C++, if you want to have disjunctive types, you can either use pointer casting, you can be try to be smart with a null pointer, you can use std variant, you can try to use optional, then you have inheritance. It's all the same, it's just disjunction. You can try to switch on enumeration, and I think there's more, but I don't remember it now. In Java, you have inheritance and switch, and right, this switch this comes into play when you want to merge the types. So if you have this with this example that I mentioned of the binary operators, so you either make them different types or you make them the same type, then you have to use the switch. So in functional languages, you have matching, which I still find too rigid and also not so efficient. And then the other important, there's too much repetition here, but another important thing is repetition. And I think repetition is solved okay. You have factors, you have C-style array, you have lists, and this works somewhat. So I think the real unsolved problem of programming language design is the union. And this applies to high-level and low-level languages. But I'm going to speak about high-level languages. Okay, so now we come a bit to my language design. So you want to define this definition. Where did it go? This one. Suppose I will show how you define it in how I propose to define this in my programming language. I think it's slide. No, then it's slide number this one. So term is these are the terms. So a term is defined as a struct, which these parentheses are just the delimiter of where the definition ends, with a function identifier and then a subterm. And the fact that it is between brackets means that it is repeated as much as you want. So a term is an identifier followed by an unbounded number of terms. Okay, then this first order logic, it is okay. It has one field which is always there, which is called selector, and just think about it like a tag or an enumeration type. Its purpose is to decide which one of the next cases applies. So a selector is just one type which has identifiers, which can be equal or non-equal, but have no other properties. So you can do nothing else with them than compare them for equality. And they're also not ordered. That's important. Okay, so you switch on this ops, and if this op is atom, then you have a pret is an identifier and an unbounded number of terms. Again, unbounded because they are between these brackets. So if you're equals, if this op is equals, then you have a left term and a right term. If the not, is there something in the chat? I'm not allowed to answer, right? Okay. So you tell me this later. Okay, you have not, you have implies, which can be left, right, or left first order, right first order. You have and or, which have an unbounded number of subformulas, from 0 to any number. And then you have the quantifiers, which have one body, and then an unbounded number of variables. Okay, this is a bit unnatural that the variable comes after the quantifier, but the reason for that is that I want efficient low-level implementation. So these things in the end are going to be implemented like C++ style factors, and then because here they have a defined an initialized part and an uninitialized part on the low level, and then this body has to be first because you wouldn't know where to put it otherwise. And this doesn't matter for the user. Okay, you may wonder where the truth constants went. There are special cases of disjunction and conjunction, just the 0 cases. Okay, so these are the basic types. I think this fits nicely on one page. This is you could see yourself writing this, but it's doable. Okay, then the subtypes come into play. So. And they're essential to the language design because they play pretty much all the possible roles that you can imagine. So, and I call them adjectives rather than subtypes because they are not real subtypes. So subtypes, they're kind of permanent. So, and yeah, right, you declare a subtype and then the subtype is everywhere through your program. But adjectives don't play this role. They are used everywhere for different things. And so the formal system for this is defined in the paper. Here I give examples. So for example, a first order logic, a first order formula can be constructed by a binary operator. You would define it like this. So this, okay, let's start here. This means being equal to and end is this selector type. So this is in the end just enumeration type, so some constant. So then and or just means being equal to and or. And then this op with a parenthesis means the of whose op field is equal to and or. So this means that this adjective has to be applied on the op field. So your formula can also be constructed by a quantifier. So then the op field must be for all or exist. Okay. Okay. Here are some more, say, deeper adjectives. So if atom defined on prop is a disjunction. It means that the op field is either atom or equals, or the op is not. The op field is not, but then the subfield has its operator atom or equals. Right? This is being an atom. It's actually literal. This is not right. This needs to be corrected. Okay, that's slide 12. Yeah. So this atom here is literal. I see this now. And the same here. So negation normal form is either a literal or the op field is and or. And then, okay, and now we come to, this is a recursively defined adjective. So a formula is in negation normal form if it's either a literal or it is an and or. And then all of the subfields must be in negation normal form. Okay, and here is the real definition of this is in the paper. But what is going on here, this subfield is a repeated field. It's this, where is it? It's this sub. And because it's a repeated field, so it can have any number of occurrences. And because of this, you cannot just say that the sub is a for all because it's a sequence. It's any number of formulas. And then you say that this is why you need this universal quantifier, just to say that each of these repetitions is a negation normal form. And this is how we call it, the negation normal form, how it applies to the quantifier, just means that the body is an NNF. Yeah, and I simplified a little bit because there is, I think you don't see this. Is it possible to see this here? No. So I can hide it. Can I hide it or not? Yeah, what you have to be, there is a sub here and a sub here, and they are in principle different. So this you have to think as, and in these adjectives also, this sub of course refers to this sub and not to that sub. And if the compiler has to sort this out, so that's surprisingly tricky. Let's put it like this. Okay. So what do the data look like? Data are just trees. Data are not aware of their type, and they also don't know which adjective they satisfy. They're just types. They're just trees, and that's all. So there are a couple of primitive types. There are unit, Boolean, character. Well, nothing surprising here, I think. This selector you have already seen in action. An index is how to say? It's like size type in C. It's just an integer that is big enough to address everything that can occur in memory. So it's a big global enumeration type. It's always written as a question mark and then something. And then the trees are just, I think what you expect that a tree is. So one of the basic types, or a tuple of trees. So then a formula could be represented like this. Okay. So this is a for all. This means that the selector must be for all. Then the fields, the variables are here because they are repeated fields. And this semicolon is just it's just a usual comma, but I use it to separate the repeated fields from the one-time fields. So you always have a sequence of scalar fields that can occur only once, and then a couple of fields that can be repeated as much as you want, unboundedly often. So yeah, you can see that. So the for all, the or again has or has only repeated fields. That's why it immediately followed by a semicolon. Then not has is this negation, and then it follows the atom, and then the formula. So this is a simple, really simple representation. And this is chosen in such a way that it has a low level, an efficient low-level implementation. The idea is that this is eventually going to be efficient in C. Okay. So then it may be useful to know that both the types and the adjectives are actually tree automata if you look at them. And so hence it is quite easy to evaluate them in the end in linear time. But linear time is still too much for an interpreter, because if you're building a big data and you say every time that you do something with it, you have to evaluate it in linear time, then you end up with quadratic time. So it's still too much for many applications. But it's okay for static type checking, I think, because static type checking you do only once, hopefully. Okay. So now we're going to come about what is actually the title of the talk. So you want to do inclusion checking between adjective, because this is really used really everywhere used. It's the core of everything. So if you have a conditional statement, like you have a formula and you want to know if it's an equality, and if it's an equality, you print it. So then you have to, what you actually check is you check that f op applies equals. Oh, by the way, you could also write this op here, of course. You could say it has op parenthesis equals. So this means that the formula is an equality. And then you can print the f left and the f right. So note that if you would write this, then you're actually writing this, that you classify it as this is a Boolean and you classify it as true. And this means has adjective. So this is notation. So if an expression has an adjective, so that's why this is first use of adjectives. Then adjectives. This is an important feature of the language, and which really made me fall out of love with C++. Is that is the checking the preconditions of fields. So this field here, this f left, is defined when the formula has when its op is equals. And there is really no reason why the compiler cannot see this. The compiler sees that you just went through this if, that it was true. So it just knows that the formula is an equals, and it knows that this field is that this f left is defined. So in order to check the precondition of an existence of a field, you can decide at compile time. That is what I hope. That is f has its op in equals, and that is left exists. So you can at compile time decide that this is guaranteed to exist. Okay. Then where did we go now? So then we have another application is checking completeness and exclusiveness of switch statements. So if you have a formula, you could switch on its operator, and you would like to know that all the cases are covered. So that is an inclusion check, because you just need to check that this that this is complete. Another important thing which I hope will work is overload resolution. So suppose you have a Tableau prover that works, you have it implemented here, that works on formulas that are in negation normal form. Now you could try to call it on a formula that is not in negation form, normal form, and you could try to define this. So f is the negation normal form of f, and then you return the tableau of f. So if everything goes well, the compiler is able to see that this one is a negation normal form, so that this one is actually this one. So this is not an infinite recursion. It's just it just uses overload resolution on the adjective. So it looks at this f. It must be able to decide if this f is guaranteed to be a negation normal form. If yes, it calls this one. Otherwise, this one, and then it sees that this one is in the anti-negation normal form. So this should work. Right, so it should be possible. Okay, then the type. So and now we come to the procedure for this. So we want to have inclusion checking between adjectives. And one reviewer pointed out that there is nothing about inclusion checking in the paper. But this is just because inclusion checking can be reduced to satisfiability checking in the standard way. Right, so if A is included in A2, then A1 and not A2 is not satisfiable. So in the end, probably the paper should have been called satisfiability checking for adjectives. But then again, the application is inclusion checking. So completeness of cases in the switch you can check by this. You just check that A is right. If you miss a case, this inclusion will not hold. So disjointness of cases can be checked by checking that two cases can never hold at the same time. Okay, so if we got a static type checking working, then all of this will be statically type checked. But there will be still the runtime type checking, because all these ifs and this if, of course, has to be checked at runtime. So we need to, there still remains runtime adjective checking. Okay, now note that I said that adjective checking takes linear time, but of course this adjective is much cheaper. This is constant time. So you could write if your formula is in negation normal form, but then you're going to pay the price for this at runtime, because it will be linear check, and then this is constant check. So, but you can if you want. Okay, then the procedure. Okay, now I introduce the procedure. The procedure is actually quite simple. And, how much time do I have to do that? I think, okay. So it works on a normal, it is a Tableau style prover. It's I think, it has not too many surprises. It works on something called pass normal form, which I think is not also not that hard. And it uses a blocking rule to cut off infinite cycles. This may seem like magic, but if you remember that there are 3 automata, then it's kind of, it is not obvious, but it's not a surprise that this works. Okay, pass normal form. So pass normal form is just negation is always applied on identifiers. Oh yeah. So this just means that you push negation through the disjunction. You push negation also. This is a field. So right. This means the field of F. This means it's not a case that the field of F is A. This means the same that that the F field is A is not the case. It means that the F field is not A. So this is just the Morgan rules. If you're not for all, not all have A, then there must be there must exist one that does not have A, and so it's all standard, I think. So Tableau rules are also not surprising, I think. So how I describe this procedure, it just works on set of adjectives. The actual implementation is more clever. It works on it somehow constructs trees and it tries to reuse as much as possible. This is in the end, of course, what makes it a Tableau procedure. If you're not reusing anything, then it's a sequent calculus. But I mean, I would almost have written sequent calculus here, but it's not exactly a sequent calculus because of the blocking rule. And in the end, I had to compromise. So I call it a Tableau procedure, even this, because even if it doesn't construct sets in the tree style. Okay, so that's, I'm getting distracted. And Tableau is closed, a set is closed if it either contains the obvious contradiction, a complementary pair, or some pair of this form where C1 is not C2. So remember that an adjective, let's say the selector constants, they are adjective. So if you, at some point you conclude that something has to be equal to two different selector constants, it cannot happen. So that then the Tableau is closed. Okay, this is the simple usual flattening rule. Okay, if you have a disjunction, then what you have to do is you remove this disjunction and then you add each of the elements of the disjunction separately to the set. So then you have n sets and you have to refute. And if you want to close the Tableau, you have to close all of them. So at this point, you have to go into a recursion or yes, and just check all these AI separately. And if there's one that you cannot close, then your Tableau is open. Okay. So if you have in your set A an identifier that has a definition, you can expand this definition, but you have to take the past normal form because it's not guaranteed, of course, that the defined adjective is in past normal form. And same if you have a negated adjective, what you do is you replace it by the past normal form of the negation. Okay. Then, okay, this is, yeah. So if you have a for all, okay, you have to remember that this for all is always a finite. So, okay, so for all is applied on repeated fields. And these repeated fields, they are finitely often repeated because they are arrays. So if you have for all A, this means either that the list is empty, that you're applying on it, or it is not empty. And if it's not empty, then A must hold for the first and for all must hold for the rest. So this is the rule for the for all quantifier. And so the exist is just the, how do you call it, the complement of this. So it means not empty and not first. This doesn't look so great. Is it the right one? I think it's okay. So if you have an exist, then the list must be not empty because otherwise it cannot exist. And then it's either the first that has this A or it's somewhere in the rest. That's the rest. That's the rule. Okay. Okay. Then comes the. I think that this is the only unusual rule of this Tableau calculus. So if none of the previous rules could be applied, and so the A contains no subformulas of this form. So this means that A doesn't speak about subformulas at all. Then A is open and we are done with it. So otherwise you have to, so you get all the, not separate because, but you take out the parts that speak about the different subformulas, the different fields. This gives you some sets, and these you have to refute all separately. Okay, so this is this. You form for each fields that you see in this A, you form the set of adjectives that have to apply to this field. This gives you this AF. Okay, and then what you have to do is you have to look at this field at its type, because types, they can have adjectives attached to them, and they need to be introduced in the calculus. Let me speak, if you speak about the op field of the first order formulas.
Sorry, your time is almost over.
How much more in concrete?
No, actually, no, 1-2 minutes.
Okay, this is my second last slide. The second, the following one is the last one.
Nice.
Okay. Because 25 here. Yeah. So So then you form this F. Okay, and now you're going to look for blocking. So if on the branch towards this AF, you somehow already had the same set that's here. So on the branch towards this, there is a set that is included in the current set, then you close it. This is blocking. So, and otherwise you have to just continue with the Tableau prover. With the rules, you have to go back to the slides on 20 and just continue. And this is conjunctively, this is important. This is not branching. So you have some sets, and if one of them closes, then the Tableau is closed. It's not like branching where it has a name. It's conjunctive branching, something like this. Okay, so this is Tableau calculus. Let's give the concluding remark. So the paper gives a bit more concrete description of this calculus, and it gives also a formal semantics of the adjectives. But it gives a little bit different data type therefore there, because it's aimed at building an interpreter there. And this procedure terminates because the set of possible A alpha is finished. A is finished, and eventually blocking will occur. Blocking is sound because if you have an open branch, you can always cut out the repetitions. It's important to know shortly that you speak about data types here. So when you follow the F, you're going into the data type. And this must stop because you're going down the tree towards the root and not to the ridge towards the leaves. So that's important that this is not modal logic. In modal logic, you have infinite paths, and this logic has no infinite paths because you're taking fields of data types. Yeah, then I implemented this procedure. Its performance is good enough to be usable. If not, I will add some type of learning to it. Okay, and then static type checking is the faraway goal, and building an interpreter is the near goal. And this seems to be now within reach with the theoretical tools that I have. So
thank you very much.
Okay, so thank you for that's it.
So we have time only just for actual time is over. Just one question. I see Andrei Ilyashin asks question in the chat. Andrei, could you please articulate your questions orally? Maybe some of them were answered. Andrei,
Yes.
we see you. Please ask questions.
Okay, can you hear me?
Yes, yes.
Hello. So my question is about what do you think about using the Coq proof assistant to represent your ideas, because you know that all of logic statements you can make there, I think could be represented by the inductively defined propositions, and the logic on the trees you mentioned can be also defined there. What do you think about it?
Yeah, so you can represent them, but programming with them is very tedious, I find. So I think the system of Coq and Haskell are not that different because it's just inductively typed trees, but then both of them use matching. But I find that's very tedious to use, very rigid. And so I want much more flexibility. And I think one can get that with the adjectives.
Okay, I see. Thank you.
Thank you very much. We have no more time. Thank you very much. Please show applause on your screen. Now we turn to the next talk by Thomas Baar. Thomas, please switch your screen, and I have to ask you whether you agree to be recorded.
Yeah, we can record it. Just my question, do you see my screen now?
Yes, we see you see your screen, and you articulate as a chair articulate. The name of the talk is on the need to support vectors and matrices in KeYmaera X system. And Thomas Baar is presented. He's joined the work with Horst Schulte. Sorry, please. Start your talk.
Yeah. Yeah. Hello, everybody. Yeah, this is a paper I wrote together with my colleague Horst Schulte. And Horst and me, we are colleagues on the engineering department. Horst comes from the control theory community, and I would consider myself to be a computer engineer. And what we wanted to achieve was that I wanted to assist Horst to formalize proof in his domain. I mean, yesterday we had the wonderful talk of Professor Petrenko, and he really argued that it's still a need to improve the tools and to bring our techniques closer to the engineers. And this is what we learned, or what we wanted to do. And when we started with tiny systems from the domain of Horst, from control theory, and wanted to formalize them. And that was quite frustrating because we did not achieve so much. And so we wrote a paper about what is all wrong in KeYmaera. But in the meantime, also thanks to an excellent review we found other papers. And so today, the world is different than 2 months ago when we wrote the paper. So what I wanted to do now is I wanted to give a kind of tutorial how we from the software verification community could go into this domain of verifying dynamic systems from control theory. And therefore, I just show you what KeYmaera is. It's an interactive prover. You can also use it for ordinary software. And then I dig into control theory a little bit, and then I show how we can apply KeYmaera on it. And at the end, I finish with some open questions and some unresolved issues. So let's start. So here we have a Java program. And what we want to achieve is we want to just add two numbers, X and Y. And what we do is just by such a while loop. So we always decrease X by 1, and at the same time we increase Y by 1. And at the end, we return the value of Y. And I don't know, I heard somewhere that is called Russian addition, but I'm not sure. I did not really found the reference. Maybe you can tell me later on when we discuss it. And if you have such a method, you have a typical contract. So you can say, okay, whenever X is positive and you start and it's an integer, right? Then at the end you get the sum of X and Y in the precondition or the pre-state is returned by this method. Or you can also drop the condition that X has to be an integer. You just say X is positive, and then you claim that the sum is returned. Or you do not have any preconditions. So, okay, the sum is always returned. And maybe if we can debate now on an informal level what we mean. So I would argue that all three contracts are true, but this depends what you mean by this contract, whether you mean termination or not. And let me show just an informal proof how you could explain it to the students why this is true actually. So here's the code, and now so this is a grid, right? And here we have the x-axis and the y-axis. And what does the program does if we start at x3 and y1, right? So whenever we go to this place, when at the end of a loop body, right? So we make some iterations. So we decrease x and we increase y. And if we are at the point that x is 0, right, then the loop is left and return the right value, right? And this is actually the same, the sum of x and y at the beginning. So if you start somewhere else, right, then we would not terminate. But this is not a problem, right? I mean, we can say, okay, the contracts are fulfilled. So now you can also apply KeYmaera for this. And in KeYmaera, we do not have that while loop. And so you would encode it by such a program. And the control flow graph would look like this. So we would go into the while loop and maybe we can go back. So this is an iteration here, that star. And then if we have a condition x equals 0, then we finish. So, and in KeYmaera, we would formulate this contract as follows. So suppose if X is at the beginning X0 and Y is Y0, whenever you execute alpha, this is the program here, when at the end you have a post condition that the new Y is X0 and Y0. So you can perfectly formulate this in KeYmaera and also prove it. And so what is the syntax of KeYmaera? So what are programs? That is assignment, you have a skip. So when you have a test, right? And so it's pretty basic. So when you have a sequential of programs and then non-deterministic choice and non-deterministic iterations. So what are the basic, the only programming constructs, and the formulas you can build up as usual, first order formulas, or as a dynamic logic with a box operator and with a diamond. So, and the box means you claim that phi holds only in the case that the post state is actually achieved. So that means that the program terminates. Okay, maybe you are familiar with this. So when you can have a proof calculus, so this is a sequence calculus, which is the basis for KeYmaera. So here we handle all this propositional logic operators, but there are also rules for handling, let's say, assignments. So you want to say at the post P of X, right? And you have an assignment. So then it's the same as just assigning this E, that expression, to a new variable Y, and then to prove just Py. So I don't want to go into details, but this is just how we could apply KeYmaera for ordinary programs. And here are some other rules for loop handling and so on. So let me switch to the next topic. Actually, we want to support Horst from a culture theory engineer, and therefore we should try to understand what his problems are and what the systems are he deals with. So, and this is a completely different story. So here we say, okay, let's take two functions from positive reals to the reals, and the functions are specified by ODEs, so differential equation, x1 prime equals x2 and x2 prime equals minus a fourth x1. So, and then we have some starting condition. What does it mean? X1 at point 0 and x1 x2 in point 0. Sorry, here we have a mistake. So this is how I would explain it my students, but Horst would just use much compact notations. So you say, okay, X prime is this system matrix, as we call it, X, and then you have some starting conditions. So this are the systems he deals with, and we can solve this ordinary equation system, and we would get such two functions, right? So the blue one is x1, so it starts in 0, goes up, down, and the orange one is x2. And we see that after some times, this is periodic, right? I mean, we have here at the end, we have, no, somewhere here we have the same conditions, so as at the beginning. So that is one way how we could visualize this solution, but there's also another way, and it's quite interesting. We could put this two values, x1 and x2, in relation. So, and then we would get such a curve, right? If it t is 0, when we have this very beginning point here, and then we go down here we are t6 and here t9, so somewhere here. And when we come back. So, and I mean, might be a surprise that this solution is periodic, and how would we prove it, or how would engineers like Horst prove it? So there are two two techniques. So one is you can have a look on the system matrix and have a look on the eigenvalues of this matrix. And depending on this, you can argue that this linear system has to be periodic. Or you can also have a Lyapunov function as an argument. You say, okay, you have to find a Lyapunov function, and the derivation of this is 0 at all time. And if you have this, then you can also argue that this solution is periodic. And here, for this case, the Lyapunov function would look like this. Okay. So we are still in the realm of control theory. So what was new for me and what is a really important tool is phase diagrams. So here I showed you already how we could show the solutions for this differential equations, but we could also write or draw such a diagram. And this shows the forces, right? Whenever you start somewhere here in the grid, right? I mean, the starting point could be taken wherever you want. Then it shows you how the system would evolve, right? And this is very interesting to look on such diagrams. And here, so the left solution is just we start here and then we go here and here and then. So that's phase diagram shows basically the forces on the system during the evolution, how it will evolve, and it's a nice visualization. And you can easily compute it, at least in the, if you go back, because you just take a x1, x2 point somewhere, right? And then you can compute the derivations, and then you show it by such errors in the force diagram, phase diagram. So and one important property of such systems is stability. And what means stability? It means for any distance epsilon, you can find a distance delta. So if you start in the delta region, then you will never leave with epsilon region. So to visualize this, you have an epsilon, you have a distance you do not want to leave, right? And then you can always say, if you have a stable system, okay, there is a delta. If you start from this delta region, then you will never leave this epsilon region. So and that was the starting point. We wanted to prove such stability arguments or properties formally using the tool, and that was not that successful, our attempt in the first place. But let me say, or let me explain what KeYmaera gives you for tools to formalize such system and to prove it. So KeYmaera can handle such systems I just explained from Horst's community, and it's really done very elegantly, in my opinion. We just introduce one new statement. So for all the other statements are what we know from programming, right? And then is one new statement, which is the so-called evolution state. And here you can just give a number of ordinary differential equations, and then you have the domain constraint. So this is the Q here at the end. And I just show you the system I just described would look like in KeYmaera like this. Or if you have it as a control flows graph, so you go here, then the system can evolve. And now it's very important that the system can always leave, right, this state and go further. And that means if we prove a post condition actually for this system, then actually we prove an invariant, because since the system can leave the state at any time, right? Then this post condition must hold at any time. So basically we can have this postcondition is used to show also invariance. So, and there is also proof calculus in KeYmaera to dealing with such evolution states, as shown here. I don't want to go into details. And the stability of a system is just this formula here for all epsilon, x is the delta, x less than delta implies if we execute alpha, then x is less than epsilon. And this x is just an abbreviation for this normal matrix, so x1 square plus x2 square. So if we take this system here and we take this formula, then we can really formally prove it using KeYmaera that this system is stable. But this was not clear to us when we wrote the paper, and then we said, oh, there's something missing in the calculus. And so what we found is the solution in these two papers, and thanks to the very great review from the first reviewer, what you pointed us to these two new recent papers. And this is, one is published at TACA, so it's our community, right? Software verification, but the others is from the IFAC community. So that is really, they published a paper in this control theory community about these systems. And what we did recently, so both papers are from 2021. We integrate new calculus rules, or introduce new calculus rules, and due to this calculus rules, we can now formally handle Lyapunov arguments in this calculus. It's quite great, but we do not have support yet for the system matrix or for analyzing the system matrix or for the mathematical approach. So here is one new proof rule for Lyapunov functions, right? Okay, I do not go into details again, but it's available now, right? So, and now we come to maybe a core of a system, or why I just want to argue that applying for verification tools becomes more and more important in Horst communities and control theory community. Why? Because now we tend to combine system. I just will explain what it means. So we have just applied now so far KeYmaera X for ordinary programs, right? We are like Java programs, so this is okay. So if you just take one dynamic system, one system of differential equations, we can also use it. But now the question is, can we also handle combinations of programs in this dynamic system? And this is something what KeYmaera offers, obviously. But it's very important to have such a tool, because this handling the combination it's really hard for control theory engineers like Horst, because I mean we know well this differential equation and solution for it, but it's very hard for them to combine them with programming language, because in order to do this, you need the semantics of programs, right? You have to know what it means, sequential execution or non-deterministic choice. And this is something I would say we are, from a computer scientists, I mean, we are the right guys to do this. So what I wanted to show you, this is running examples from the paper. So we have system one, this was this tiny system I just argued, and now we define another system, and the only difference is that we change the coefficient here in the system matrix, right? And you see the solution is somehow different, of course, but it's basic. It's same, still a periodic function, and it has such a phase diagram. So it looks similar, right? But now we have the point. I mean, both systems are stable, right? I just have proved it for this one, and for this it's the same. But the question is, what about the combination of this both systems? If we combine them, right? And we have investigated two cases. So first, there is a condition if x1 times x2 is greater 0, right? So in the first case, in this case we take cis1, cis2, and in the other case is cis1, right? And the second combination is vice versa. And now the funny thing is that the first switching system, as we call it, is still stable, but the second is not stable. And of course, we would be interested to prove also the stability. So let's have a look on the first switching system. So if we have a phase diagram, right, when we see the forces, and we would go closer and closer to the 0 point, right? And in the second one, we go more and more far away from this middle point. So this are we can see it with a phase diagram, but of course we would also like to prove it. And here is the KeYmaera encoding for the first case, the first system that remains stable, and it's not complicated as a KeYmaera, but we can KeYmaera X is able to formally prove that this stable system is still stable, and this was done in this paper here. And it's funny enough that we took this very same system as with the very same example. I mean, we did not know each other before, but we took the very, I mean, it's a well-known example in this community, right? But to show that switch system can become unstable, but funny enough that the formal proof is also presented there. So, but there's still some open research, something to do. And what we cannot formulate that yet is that the system is asymptotic stable. And asymptotic stable means that it's stable and that the value for that x converges to a certain value, like 0, right? So, and I would like to formulate it still as an open problem, and maybe to you, or we can discuss it. So this is stability, right? For all epsilon, x is delta, and if you execute alpha, then you will remain always below epsilon. But how can you formulate that somewhere in the future you will become as close as to 0 as you want? So not for a fixed epsilon, but that the epsilon might become always close. So actually this is an invariant here, stability, but asymptotic stability is somehow you say something, wherever you start, you end up in a certain point or become close. So we have to say some liveness or some, so eventually, right? You have to say something about eventually, but you cannot use this box diamond operator here. So I think that would not work out. So for me, it's still open. So I come to my last slide, a summary. So what I wanted to tell you that we have a tool, KeYmaera X, that is able to integrate traditional programming concepts with dynamic system, with differential equations, and also offers a calculus for it. And very recently, this year, we introduced calculus rules that are able to handle Lyapunov arguments, right? That something remains stable or remains slow. But what is not supported yet is that you can say I want to look on the eigenvalue of the matrix, like as Horst would do it, right? As an engineer. So this is not supported, and I had some personal communications with the authors of KeYmaera, and they say we are not going to integrate this. That seems to become much more complicated and their argument is you can always have a look and look for a Lacuna function. And another thing is the asymptotic stability. I was not able to formalize it, right? In such a dynamic logic, and yeah, I would. This is still my open question. So thanks for your attention.
Thank you very much. Who want to ask questions, please? No questions in chat. Please switch on your microphone when you want to ask. Andrei, please. Lashin.
Yeah, thank you very much for your speech. I would like to ask you about what is the main principle to reason about real number calculation. I mean, to reason about real number properties, you need something under the hood that can deal with real or at least rational numbers. How can you reason about this?
I mean, KeYmaera is also based on algebraic systems, so we have some provers for it, right? And this is, I mean, you don't have a calculus rule saying that 3 plus 5 is 8. So this comes from back-end provers. It's this information, right?
Yeah. Okay. So in this representation axiomatic, how does it correspond with the real calculus in some particular programming languages? For example, if you take some machine-based real number representation, you can never get the same result as for ideal real or rational number. How can you extract the program? How can you guarantee that your real dynamic system will get the same result, even if you prove it?
Okay. So you mean that the arithmetics and if you implement it is different from mathematics, right? So I think this is not catch-up. So this is the real numbers we have in KeYmaera as the concepts, the mathematical concepts of real numbers, right? No approximation of it, and yeah. How to say it? I mean, at least I'm not aware of it. I mean, if you approximate some computations, then you might, when the system might behave different from what you have modeled in KeYmaera. Yeah, that's right.
Okay, thank you.
Hi, Thomas. Thank you for your talk. Very exciting talk, and seems you've learned a lot with your co-author. And it's nice that they already included Lyapunov function into the calculus. So it is news for me, and thank you for your presentation. And now I know it. But the question. I've got some questions, but the first one is how to prove instability of the system. Because if you prove stability, you introduce a function and you prove the stability according to the function. But how to prove that the system is unstable?
Yeah. Okay, what does it mean unstable? I mean, the stability is for all exist a delta, right? So when instability would be the negation, right? So for all so there exists an epsilon for that you cannot find a delta.
But maybe
so that you would try to prove a negation. So that's an interesting question, how whether you can achieve that, right? So as a kind of counterexample, right? So that's a good point. So did not have a look on it that you can really see unstable. But okay, maybe. So if you have a look on such a phase diagram, right, when you see that it's unstable, right, it's not surprisingly, but maybe you do not have always such nice representation of your system like this one, right? So because usually you are interested in stability, so that whatever. So yet that yes, your system will not go into a dangerous area because it will become very high or some values, right? So I think stability is more important than instability, but we can try it. But it's a good point. Maybe we can include it.
Thank you very much. We are now out of time. Let's applause to our presenter, Thomas. Thank you very much for an interesting talk.